Welcome to a second example on how to determine the curl of a two-dimensional vector field. Remember, the curl of a two-dimensional vector field is a scalar function defined here, while the curl of a three-dimensional vector field is another vector field. So because we have a two-dimensional vector field, using our formula below, notice how p is equal to 3x sine y, and q is equal to 2y cosine x. So let's go ahead and use our formula here to find the curl of the given vector field, and then we'll determine the value of the curl at 2 points in the given vector field, then look at it graphically. So the curl of the two-dimensional vector field f is equal to the partial derivative of q with respect to x minus the partial derivative of p with respect to y. So in our case, we'd have the partial derivative of 3y cosine x with respect to x minus the partial derivative of 3x sine y with respect to y. So the partial of 2y cosine x with respect to x would be 2y times negative sine x, or negative 2y sine x, minus the partial of 3x sine y with respect to y, which would be 3x times cosine y. This doesn't simplify, and therefore this is the curl of the two-dimensional vector field. Now remember, the curl of the vector field measures the rotation or spinning effect at a given location. So let's go ahead and evaluate the curl at 2 points in the given vector field, then look at it graphically. So let's find the curl of f at the point pi comma pi. Let's also find the curl of f at the point negative 2.5 comma 2. So the curl of f at pi comma pi is equal to negative 2 times pi times sine pi minus 3 pi times cosine pi. So simplifying, we're going to have negative 2 pi times 0 minus 3 pi times negative 1, which equals positive 3 pi. And now let's find the curl of f at negative 2.5 comma 2, which is equal to negative 2 times 2 times sine negative 2.5 minus 3 times negative 2.5 times cosine 2. Now we're going to determine this value with approximately negative 0.7272. So notice at this point the curl is positive, at this point the curl is negative. So let's take a look at this graphically. The graph of the given vector field f is graphed in red. This point is the point pi comma pi. So because the curl at this point is positive, to determine the direction of rotation, we would take our right hand and point our thumb upward, and if we close our right hand, our fingers curl in the direction of rotation, which in this case would be in this direction here. So if the curl is positive, the rotation is counterclockwise, and the absolute value of the curl tells us the strength of the rotation, or how fast it would rotate. This point here is the point negative 2.5 comma 2. Notice at this point the curl is negative, which means to determine the direction of rotation, this time we would take our right hand and point our thumb downward, and as we close our right hand, again our fingers curl in the direction of rotation, which in this case would be a rotation in this direction. So notice how when the curl is negative, the direction of rotation is clockwise. I hope you found this helpful.